Hi everyone, I'm Suki. Today in this presentation, I'm going to tell you three applications of ferromagnet. Firstly, a ferromagnet can be used as a core in a transformer. A ferromagnetic core is usually made up of iron. Its function is to channel the magnetic field lines from the primary coil to the secondary coil. In fact, a transformer usually consists of a primary coil and a secondary coil wound on an insulated soft iron core. Transformer works based on electromagnetic induction. A primary coil is normally connected to an alternating current power source. When an alternating current flows in the primary coil, a changing magnetic flux will be generated around the primary coil. So when the current increases, magnetic field increases and vice versa. And when the current reverses, the magnetic field changes direction. So this changing magnetic field flux produces within the winding of the primary coil is transferred through the core and goes through into the winding of the secondary coil. And this is where we can see the electromagnetic induction. The changing magnetic flux is then cut by the secondary coil and hence induces an electromotive force in the secondary coil. And we can see the light bulb lights up. So there are three reasons why we are using iron core. Firstly, it has high permeability. In fact, the ferromagnetic property of iron core causes the internal magnetic domains of the iron to line up when a small driving and magnetic field is produced by the current in the primary coil. The effect is that the magnetic field can be multiplied by a factors of tens and even thousands. The relationship between the magnetic field and the permeability of the iron core is stated here. So B is the magnetic field, K is the relative permeability of iron, showing the magnifying effect of iron core. Mu naught is refers to the permeability of free space. Normally, paramagnetic or diamagnetic material has a permeability whose values are very close to mu naught. So if you apply mu equals to mu naught, you will get K equals to 1. So there will be have no magnifications of magnetic field when using paramagnetic or diamagnetic material. On the other hand, pure permeability of ferromagnetic material is actually very large. Okay, you can see in this table, the relative permeability of iron core is actually 200. So iron core can obtain large magnetization in response to an applied magnetic field. For example, in this case, if you are using ordinary iron core, you can expect a magnification of 200 compared to the magnetic field produced by the solenoid current with just using an iron core because the relative permeability of magnetic iron is 200. Okay, so in this picture, you can see that a lot more magnetic field line is produced when using iron core, while less magnetic field line is produced when you are using air as the core in a transformer. Secondly, iron core has low retentivity and coercivity, thereby reducing the hysteresis losses. Low retentivity refers that iron can be magnetized but do not retain its magnetization, while low coercivity refers that iron requires a small magnetizing field to demagnetize it. In hence, low retentivity and coercivity will form a narrow hysteresis loop as shown in this picture. And the area of hysteresis loop actually represents the energy loss in one cycle of magnetization and demagnetization. So, a narrow hysteresis loop implies that only a small amount of energy is dissipated in repeatedly reversing the magnetization. And in transformer, the lost energy is normally given out as heat, and it's normally refers as hysteresis loss. So when using iron core as a soft electromagnet for a transformer, it can minimize energy dissipation with alternating magnetic field lines due to the application of alternating current at the primary coil. Lastly, iron core has low magnetic flux reluctance. Magnetic flux reluctance is just like a resistor that resists the flow of magnetic field lines Yeah. So a magnetic reluctance is inversely proportional to the permeability, as we mentioned at the first reason. So magnetic flux, it will concentrate it around the path with least reluctance. Air and vacuum normally have high reluctance. So you can see in this picture, which is using iron core as the, which is using air as the core. So the magnetic field line will be dispersed in the air outside the primary coil. So only a few magnetic flux can be transferred to the secondary coil. On the other hand, if we are using soft iron, which has low reluctance, all magnetic flux can be concentrated outside the coil, and all the magnetic field line can be channeled to the secondary coil by the iron core. So almost zero leakage of magnetic flux when we using iron core in a transformer. The second application of ferromagnet is it can be used in magnetic tape recording. So this is the tape head, this is the tape, and this is the core. Okay, a tape head is normally made up of ferromagnetic material, which is iron, and a coil of wire around the ring carries the oscillating current to produce the magnetic field proportional to the signal to be recorded. This is the magnetic field produced. And the tape as the recording medium typically made up of iron oxide particles. Okay, so the oxide particles themselves, they do not move during the recording, but actually it's their magnetic domain are oriented by the magnetic field produced on the tape head. So this is the process of magnetic field recording. Firstly, before passing over the record head, a tape passes over an erase head, which applies a high amplitude and high frequency of alternating current magnetic field to the tape to erase any previously recorded signal by randomizing the magnetization on the tape. Then the tape will pass through the record head. A high frequency of biasing signal, okay, will be applied to the record head along with the signal to stir the magnetization on the tape. So at here, the magnetic domains of the iron oxide are aligned to record any input signal from the tape head. Lastly, when a magnetized, now the tape is magnetized. So when the magnetized tape passes under the playback head of a tape recorder, the ferromagnetic material in the tape will be magnetized, and that magnetic field will penetrate to the coil of wire which is wrapped around it. So any change in the magnetic field will induce a voltage in the coil based on the Faraday's law. And this induced voltage will form an electrical image of the signal, which then is recorded on the tape. So why we are using iron oxide in magnetic recording? The only reason is that it has high retentivity and cohesivity. So high retentivity means that the signal can stay very well on the tape after being recorded, and a large signal can be produced after the playback head for the playback head to pick up. On the other hand, it also has high intrinsic cohesivity. It means that large hard iron require large magnetizing field to erase head to erase previously recorded signal, hence result a high stability of signal against demagnetization. So it's due to that hard iron core is very desirable for magnetic recording and also memory device. Lastly, ferromagnet can be used in explosive-driven ferromagnetic generator. Normally, we name it as EDFMG. So EDFMG is actually a device that makes use of the impact of ferromagnetism to achieve the transduction from magnetostatic energy to electric pulse energy. The EDFMD actually consists of a ferromagnet, which is usually a neodymium, an alloy, a high explosive charge, and a pick-up coil. So a shock wave will be generated by the explosion, and then it will destroy the magnetic domain in the ferromagnet. This causes loss in the magnetic field. The process results in a rapid demagnetization. In accordance to the Faraday's law of electromagnetic induction, this rapid and sudden change of magnetic flux will then induce an EMF in the conductor, thereby forming a high pulse current in the external circuit. Okay, so these are the three applications of ferromagnet in my presentation. Thank you for listening.